In the previous module, we looked at graphical methods for dimensional synthesis of crank rocker mechanisms. We assumed that we were given a desired range of motion for the rocker. There are two characteristics of these methods that we studied. First, you had to make some choices. For example, you chose the length of the rocker link. Second, the methods indicated that the design process may have to be repeated based on the evaluation of the design. We had seen two possible metrics for evaluating a design. The first one was the Grashoff condition. We wanted to check whether the mechanism was Grashoff or not. This is because we wanted a crank rocker mechanism, and if the mechanism was non-Grashoff, then there would not be any crank. The second check was about transmission angles. At this point, the key high-level bit that I want you to take away from the procedures is that design involves choices and design is iterative. You may have to do multiple iterations before you come up with a satisfactory design. This is our plan for this module. First, we will look at two position synthesis problems for crank rocker mechanism, where the position of the rocker is given to us. Note that this is different from what we did before. In the previous module, the rocker range of motion was given to us. However, now two positions of the rocker will be given to us, and that will lead to a little bit of difference in the graphical construction procedure. Then we will do 2 and 3 position synthesis for 4-bar mechanisms with given coupler positions. So let us look at the first problem. We are given two positions or poses of the output rocker, and we want to design a 4-bar mechanism that drives the output link or the rocker through the given positions or poses. Furthermore, the crank will be driven by constant motor input. So how do we prescribe the positions or poses of the output rocker? As we had discussed in the previous module, let's say the rocker is some rigid body. Then if I pick any line segment on the rigid body, say CD, and prescribe its two positions, then I am prescribing the two positions of the rocker. So what does it mean to prescribe this line segment CD? It means that you prescribe the coordinates of point C, which is XC, YC, and we prescribe this angle theta, with theta measured positive counterclockwise from the x-axis. So we will be given two sets of numbers, XC, YC, and theta. Our first step is to draw the line CD on the rocker in its two desired positions, C1D1 and C2D2. Note also that when you are choosing CD, you are essentially choosing the length of this line segment. Then we connect C1 to C2 and we connect D1 to D2, and we draw two mid-normals or perpendicular bisectors of the segment C1, C2 and D1, D2. So how do you draw a perpendicular bisector? With a compass, you take C1 as center and radius C1, C2, or any radius that is greater than half of C1, C2, and you will draw two arcs. Then with the same radius and center C2, you draw two arcs. Join the points where the arcs intersect. That will give you the perpendicular bisector. The intersection of these two mid-normals or perpendicular bisectors is the fixed pivot O4. Why is that true? Recall that the whole link rotates about this fixed pivot O4. Therefore, any point on the link will be on a circle centered at the fixed pivot O4. So the point C will be always moving on a circle centered at O4. Point D will be always moving on a circle centered on O4. From elementary geometry, we know that if C1 and C2 lie on the same circle, then the center of the circle lies on the perpendicular bisector of the segment C1, C2. Similarly, if D1 and D2 lies on a circle, the center of that circle lies on the perpendicular bisector of the segment D1, D2. Therefore, it follows that the fixed pivot O4 has to be at the intersection of these two lines so that it can lie on both lines. Now we want to make sure that the line segment CD moves just between these two positions, C1, D1 and C2, D2. We will select any point B1 on the line O4, C1 and locate the corresponding position B2 on the line O4C2. B is the choice of my moving pivot, and O4B1 or O4B2 will be my rocker link. We connect B1, B2 and extend it. Any point on this line will be my other fixed pivot O2. Note the similarity here to the first construction that we did on the last module. Once you have chosen the moving pivot B, the problem becomes the same as the first problem in the last module. Then we draw a circle of radius B1, B2 by 2 that is centered at O2. Therefore, our mechanism becomes O2A is the crank, AB is the coupler. Here you can take A2B2 as the coupler length, O4B is my rocker, and O2O4 is my ground link. Since we want a crank rocker mechanism, therefore we have to check if the mechanism is Grashoff. If it is not, we have to go back to step 4, that is select the point B again and redo from step 4 to step 8 until we are satisfied. We also have to check the transmission angles of the mechanism. You should note here that from steps 4 to steps 8 is identical to the first problem that we did in the last module, where we had a given range of the rocker motion. Here, although the angle is not given to us, we found the angle by the construction in the first 3 steps. We will now look at dimensional synthesis of 4-bar linkage for motion generation, where the motion of the coupler is specified. Typically, a set of 2 or 3 positions or poses of the coupler link are given, and the goal of the design is to determine the location of the 2 moving pivots on the coupler link as well as the 2 ground pivots that connect the input and output links to the ground. One common way to solve the design problem is to select the locations of the moving pivots and then compute the location of the fixed pivots either graphically or analytically. We will look at the graphical method in this module and we'll look at the analytical methods later. We will study 2 problems. First, we'll study the 2-position synthesis problem, and then next we will study the 3-position synthesis problem. So what is the problem statement for the 2-position synthesis problem? Given 2 positions or poses E1 and E2 of the coupler, which is shown in the picture on the left, what you want to design is a 4-bar mechanism that ensures that the coupler reaches poses E1 and E2 through a continuous motion, and we also want an input dyad that ensures that the coupler motion is limited between the poses E1 and E2 and doesn't go beyond these poses. So what does it mean to give a position or a pose of a coupler? In the figure on the left here, XOY is my world frame or my global coordinate system. This here is my body frame, B. The shape of the coupler I have drawn arbitrarily. It can be anything. I have just made it this shape here. The frame B is attached to the coupler. So here, by pose of a coupler, we mean that the coordinates of the origin of B is given, XY is given, and the angle that the x-axis of B makes with the x-axis of W, that is theta 1, here is given. So I can call this x1, y1 with a subscript to show that it is the position 1. For the position 2, x2, y2 will be given, and the angle theta 2 will be given, where x2, y2 is the position of this origin here. Problem 1 can be rewritten as designing 2 moving pivots on the coupler and 2 fixed pivots such that the resulting 4-bar mechanisms ensures that the coupler reaches poses E1 and E2 through a continuous motion. Our strategy to solve problem 1 will be to select or choose 2 moving pivots on the coupler and compute the position of the fixed pivots or graphically construct the position of the fixed pivots. For example, we can say let this point and this point be my moving pivots. In the second configuration E2, it will look like this. Note that since we know x1, y1 and theta1, and we are choosing the points C1 and D1 on the coupler, that basically means we know C1 and D1 in the global frame or in the frame W. Similarly, we know C2 and D2 in the global frame or frame W. And when I say known, I mean you can just calculate it or it will be given to you directly. The first step in graphical two-position synthesis is to draw the link CD or the coupler in its two positions C1, D1 and C2, D2. Recall that C1 and C2 are the positions of the same moving pivot at two different configurations of the coupler. Similarly, D1 and D2 are two positions of the moving pivot at the two different configurations. So we'll first connect C1 to C2 and D1 to D2, which are shown by the red lines here. Then we will draw a perpendicular bisector or mid-normal of C1, C2 and a perpendicular bisector or mid-normal of D1, D2. So this has to be perpendicular here and these two have to be equal. Now, any point on the perpendicular bisector of C1, C2 can be chosen as a fixed pivot O2. And any point on the perpendicular bisector of D1, D2 can be chosen as the fixed pivot O4. Why is this true? Because, as we have stated before, the moving pivot C always moves on a circle with the center at a fixed pivot. So since C1 and C2 are on the same circle, the perpendicular bisector of C1, C2 will contain the center of the circle. Since we have no other information, we can choose any point and that should be a candidate point for my fixed pivot O2. The same reasoning works for selecting the other fixed pivot O4. So my final mechanism here is O2, O4 is my fixed link, O2C is one link, O4D1 is the other link, and C1D1 is my coupler. The figure on the left shows the construction in the previous slide. Note that in this case, it is not necessary that the mechanism has to be a Grashoff mechanism. What is necessary is that the mechanism will continuously move from C1D1 to C2D2. This can be checked with position analysis or a simulation software for mechanisms that is built based on position analysis, and we will talk about this in the next lecture. So in this design process, what we ensured was that the coupler are at the positions C1D1 and C2D2. We have not ensured that there is a continuous motion that takes the coupler from C1D1 to C2D2. If we check and find that there is no continuous motion that can take the coupler from C1D1 to C2D2, or the continuous motion contains something known as a toggle configuration, which we will define later, then we will repeat with different choices of O2 and O4. The figure on the right here shows the mechanism that we just designed at its two desired positions. Once we have designed a mechanism such that there is a continuous motion that takes C1D1 to C2D2, the next part will be to ensure that the motion of the coupler link CD is between C1D1 and C2D2. So this becomes the extreme positions of the linkage CD. In other words, my link 2 has to move from this configuration here to this configuration. If you think about it for a moment, you should see that what I am prescribing here now is that I know the range of motion of the link O2C, and I want to design another mechanism so that the link 2 or the link O2C moves between O2C1 and O2C2. This will ensure that the coupler moves between C1D1 and C2D2. To do this, we'll first draw the 4-bar in the two positions, or essentially we need to draw the link O2C in two positions, O2C1 and O2C2. Then we select any point B on the link 2, and B1 and B2 are the two positions of the point B at the two extreme positions of the link 2. We connect B1, B2 and extend. Any point on this line will be our other fixed pivot, and we call this O6. We draw a circle with radius B1, B2 by 2 centered at O6. The radius of this circle is the crank, or the length of the sixth link. O6A now becomes my crank or link 6, and AB is the other link or the link 5, which will essentially connect the crank to the link O2C and drive the link O2C. Note that point B is a choice here. I could have selected the point B anywhere on the link. It didn't need to be on the line O2C1. The second point to note is that after we design this new driving diode, we have another 4-bar mechanism O2, O6, A, B. This 4-bar mechanism needs to be Grashoff. If this 4-bar mechanism is not Grashoff, then there will be no crank. So after you design this diode, you have to check that the 4-bar mechanism O2A6AB is a Grashoff mechanism. You also need to check the transmission angles of this mechanism. Note again that the design of the driving diode is essentially the problem 1 of the previous module. You should also note that the link O4BC is a ternary link, and this is a 6-bar linkage. It's a Watts 6-bar linkage. You should convince yourself that the degrees of freedom of this mechanism is 1, and you should also find out which inversion of the Watts 6-bar linkage this mechanism is. Let us now look at the 3-position synthesis problem. We are given 3 positions, E1, E2 and E3. That means we are given the coordinates of this origin here, x1, y1, this angle theta 1, x2, y2, angle theta 2, x3, y3, and the angle theta 3. Our goal is to design a 4-bar mechanism that ensures that the coupler reaches configurations E1, E2, and E3 through a continuous motion. Our second goal is to ensure that we can design an input diode so that the coupler motion is just limited between E1 and E3. This design problem 1 can again be rewritten as designing 2 moving pivots on the coupler and 2 fixed pivots such that the resulting 4-bar mechanism ensures that the coupler continuously goes through E1, E2, and E3. And just as our previous problem, our high-level solution strategy is to select or choose 2 moving pivots on the coupler and then compute the position of the fixed pivots or construct the position of the fixed pivots graphically. As an example, we can choose the 2 pivots to be at these 2 points, let's say A1 and B1, and choosing the 2 pivots basically means we know this vector here and this vector here. I hope that it is clear to everybody that once I know A1 and B1 in the coupler reference frame, I can use simple vector addition to get OA1 and OB1. It means that I know the moving pivots in the global frame, or my moving pivots are specified in the global frame after I make the choice of the moving pivots. So in the first step, we will draw the moving pivots at the 3 positions, A1, B1, A2, B2, and A3, B3. A1, B1, A2, B2, and A3, B3 is the coupler at the 3 positions. We join A1, A2, join A2, A3, take their perpendicular bisectors, and wherever those 2 perpendicular bisectors intersect, that is my fixed pivot O2. Why is this true? Because note that A1, A2, A3 are the positions of the moving pivot as the mechanism moves. So they have to lie on a circle that is centered at one of the fixed pivot. If you know 3 points on a circle, then by elementary geometry, the perpendicular bisectors of A1, A2 and A2, A3 intersect at the center. We repeat the same process for the other moving pivot B. Join B1, B2, B2, B3, draw the perpendicular bisector of B1, B2 and B2, B3. They intersect at O4. The same logic as before is valid for construction of O4 also. Therefore, O2A1 and O4B1 are my 2 links that are connected to the ground. AB is my coupler and O2O4 is my fixed link. Note that we have just ensured that the link AB reaches these 3 positions, A1, B1, A2, B2 and A3, B3. This construction procedure does not ensure that the link AB moves continuously to go through the positions A2, B2 and A3, B3. So we have to do position analysis to ensure that continuous motion between these 3 positions are possible. The second thing to note is this 4-bar mechanism can either be Grashoff or non-Grashoff. It doesn't really matter as long as continuous motion is possible. If continuous motion is not possible, then we need to iterate. And in this case, the iteration will be based on different choice of the moving pivots A and B. The steps described in the previous slide are just shown here. This is a picture that shows that depending on the positions of the moving pivots, your O2 and O4 can lie on 2 different sides of the links. Now the picture on the right shows the finished mechanism in one pose or one position. Note that now if we have to ensure that the link CD moves from C1D1 to C2D2 to C3D3, or the coupler moves through the 3 given positions, then we have to ensure that the link 2 moves between the position 1, that is O2C1 and O2C3. So the problem of designing the driver diode again becomes the first problem in the previous module. So first I have drawn the 4-bar linkage in the 3 positions, and then I choose a moving pivot on the link O2A1 and I call it C. C1, C2, C3 is the position of the same moving pivot at 3 different positions of the link O2A1. Then we will join C1, C3 and extend it. So why do we join C1, C3 or not C2, C3 or C1, C2? It is because the link O2A has to move between O2A1 and O2A3. These are the 2 extreme positions. So we have to connect the 2 extreme positions. O2A2 is an intermediate position, or C2 is an intermediate position. Again, any point on this line C1, C3 extended will be a fixed pivot O6 for the driving diode, and take a circle of radius C1, C3 by 2, and the points at which it intersects are the positions D1 and D3 of the moving pivot of the crank. So here I will draw the crank at the position 2 so that the straight lines don't overlap. But O6D2 is my crank and DC or D2C2 is my link that is connecting to the link O2A. Again, the overall mechanism is a 6-bar mechanism, and the 4-bar subchain O2, O6, D, C. This has to be a Grashoff mechanism. If this is not a Grashoff mechanism, then we do not have any crank. If we do not get a Grashoff mechanism for O2, O6, DC, then you have to choose another point O6 and repeat. After making sure that O2, O6, DC is a Grashoff mechanism, you also need to check the transmission angles of this 4-bar mechanism. If you do not have the desired transmission angles, then you have to choose another O6 and repeat till you have a satisfactory driving diode.